to welcome you to our second Faculty Centennial Lecture. This series celebrates 100 years of scholarship at St. Joseph's College. And at this important milestone in our history, it's most fitting that we highlight one of our core values, the life of the mind and the pursuit of knowledge. In this area, our faculty provide the leadership, guiding students as they formulate questions, design experiments, engage in research, and develop their creative voices. Our speaker tonight is an exemplar of the teacher-scholar, a professor whose curiosity is matched by few, a true model of intellectual values. But you're going to be hearing more about Professor Holtzman from Joe Ross in a few minutes. While the lecture series highlights the scholarship of the current faculty, each lecture is named in honor of a former faculty member who made contributions that we build on today. The Centennial Lecture in Mathematics is in honor of Sister Pat McKenna, who served as assistant professor in the mathematics department from 1978 to 1988. And it is most fitting that we have Sister Nancy Gilchriest, who I believe is her former student, to present the tribute to Sister Pat tonight. Sister Nancy graduated from St. Joseph's College in 1983 with a bachelor's of science in mathematics, and later earned a master's degree in mathematics education at Columbia University Teachers College. She went on to earn her doctorate in educational administration and supervision at St. John's, and she then taught high school in the Boston area. She later served as the chairperson of the Department of Education at the College of Notre Dame in Maryland, and it has been our good fortune at St. Joseph's that she returned to us in 2005 and currently serves as an associate professor and the chair of the Adolescent Education Department. So with that, I will turn over the mic to Sister Nancy to give her tribute to our honoree at tonight's lecture. Thank you.
Thank you, Dr. Rehmann. When Irish eyes are smiling, I would ask that everyone who knew Sister Pat McKenna, would you please raise your hand? And those who have raised their hands, are you surprised I started with that song? You shouldn't be if you knew Sister Pat. And if you look at these photos, you can tell why I've said it. Because when I first encountered Sister Pat as my math teacher in 1980, my thought was, these Irish eyes are really smiling. And for those non-math people in the room, you need to know that those Irish eyes smiled with every equation, whether it was quadratic or differential. As a math major, it was a delight to have Sister Pat as the teacher of two different classes. And my clearest memories of her include her love of mathematics, her clarity of explanation, and most importantly, her love for her students. Centennial celebration, because to me, Sister Pat exemplified the college's motto, Esse non vedere. Her Irish eyes smiled because she loved all she saw. In a letter from Sister George Aquin, the St. Joseph's College president, to the college community in September of 1988, Sister stated, Sister Pat communicated to all of us a love of life, a great cheerfulness, and an optimism in the face of difficulties. May her memory live on as we strive to follow her loving example, and may our eyes smile as well. It is now my pleasure to introduce Dr. Joseph Ross, Associate Professor of Communication Studies.
Thank you, that was lovely. When you've been married for more than 25 years, as I have, your spouse generally loses the subtleness and the different ways to tell you what she thinks. So when I told my wife that I was given the opportunity to introduce this brilliant mathematician, she grimaced, She laughed a little bit and she said, you know, it sounds like there's going to be a lot of numbers and formulas and equations. Are you sure they want you to do it? Well, don't worry. I'm assured that there are not a lot of numbers and equations and formulas with Dr. Seppala-Holtzman. And yes, I am sure that I'm very proud to be able to introduce my friend and colleague to you tonight. You have to be careful what you tell us, David, because David has told us a childhood story that impacts how he approaches even his work today. As a boy, he was told that every snowflake is unique. But instead of accepting that as a fact, he started to ask questions. He said, who says so? And how do we know that? And what's the science behind it? And can you prove it? And thus began a lifetime of asking questions, exploring logic, and searching for the truth, ultimately through the field of mathematics. In your program, you'll see the details of his outstanding career, and I won't repeat them all. But I will highlight that he earned his doctorate in mathematics from the University of Oxford in Great Britain. He joined the faculty of St. Joseph's College in 1981, and he's held several significant leadership positions in the local mathematical community. He also spent a semester as a scholar in residence at the Current Institute with NYU. David is the recipient of both the Distinguished Service Award and the Excellence in Teaching Award conferred by the New York Metro Mathematical Association, which is a mouthful, and he's also the author of 17 scholarly papers. So despite what my wife thinks, I analyzed the data, and I deduced David's a really smart guy. But there are a lot of smart people in the world, and David separates himself in many other ways. You won't be surprised to learn that the paper for which he is most proud is the one that he co-authored with one of his students. One of his seniors told me, Dr. Seppala-Holtzman has very high standards, but he's also incredibly patient. He works just as hard as he makes us work. Another student continued, he makes math matter. You think it might be something you'll never use, but he makes it real, and he shows that it's part of your everyday life, and that is why he is the best. One of David's colleagues finds him most impressive not as a teacher, but as a mentor who values logic and reason. David offers a problem of the month, where the prize is not a Dunkin' Donuts card or extra credit or anything like that. The prize is virtue itself. And this is a reward that certainly illustrates his love of learning. Finally, now pay attention. David is a certified scuba diver. He plays the cello. Badly, he tells me, but I doubt it. And he learned to speak Dutch by watching Dutch television and reading trashy Dutch detective novels. So I began this introduction by kidding about how could I or anyone outside of the field really engage with David. And the truth is, what makes him special is not really just his mastery of his field, but it's his passion for people and for true learning. It's his ability to communicate his message in a way that is engaging, it's articulate, it's of good humor, and it is in a way that truly matters. Please welcome Dr. David Seppala-Holtzman.
Thank you so much. I always find it rather disconcerting when your own introduction is a hard act to follow, but I'm going to certainly give it my best shot. Let me see if I can get my screen up here. And talk amongst yourselves. There you go. That's quite all right. Okay, there we go. First, I want to thank Joe for that really nice introduction. As I say, it's a hard act to follow, but I'll give it my shot. I also want to thank and acknowledge the other members of the Centennial Lecture Committee. Joe is a member of it, Michael Hannafy, Raymond DeAngelo, and Jamie Vaca. And without these people, this would not be happening. So thank you all. I also want to thank Sister Nancy, because that was firstly a lovely tribute. And I should also tell you that Sister Nancy was also an ex-student of mine. Yes, she was. And she has transitioned beautifully from an extraordinarily wonderful student to a highly valued colleague. And I just love seeing that transition. Thank you, Sister Nancy. Speaking of ex-students of mine, I have quite a number of beautiful faces in this room, which I simply must acknowledge. So I would love to have all of my present and ex-students please stand. What a beautiful sight. Just a moment ago, we heard a tribute to Sister Pat McKenna, and that was our way of honoring the past. The people you've just seen stand and sit, in my view, are the future, and I see the future as extraordinarily rosy, given what I'm seeing here. Know that I love you. This is for you. After that moment of embarrassment by displaying all this emotion, which is uncharacteristic of me, I wish to make amends, and the best way that I know how to make amends is by praising pure reason. I also offer my apologies to Immanuel Kant, but I understand he doesn't care any longer. So I've stolen his title, but there it is. At the bottom of the screen, you will see a web address. That's my web address. And if you go there and look at the landing page, you will find downloads on the menu. If you go to downloads, you will find this presentation and many, many others in the unlikely event that you ever want to see it twice. But there it is. And speaking of presentations, let's get this party started. Okay, so we are going back to ancient Greece, and we are going back in time to roughly 600 BC. And there, by previous arrangement, we're going to run into a guy named Thales. I know it looks like it's Thales, but I believe it's Thales. And he is considered by most historians to be the father of demonstrative mathematics. He's the one who gave us theorem and proof. That was a fantastic gift, theorem and proof. Over the next 8 centuries, the Greeks cultivated and they nurtured this incredibly powerful form of human reasoning, and it was a gift to the world of unbelievable, extraordinary value. However, impressive as it is in fact not my topic for tonight. So, sorry. However, it's related. I want to talk about the ancient Greeks and the field of astronomy. Well, the Greeks, like almost all ancient cultures, cast their eyes to the heavens. Oh, please. Okay, somebody steal that car. Okay, that's all right. Okay. No, okay. So, while that is happening, that was planned, by the way. That was planned. That was right. Back to our story here. We have an interest in the heavens. Clearly, that's a natural thing for ancient people to be doing. What's going on here? What's the nature of the Earth on which we stand? What's going on with the sun? What mysteries does the moon hold? What can we deduce about these things? These are surely mysterious entities. What can we deduce? Well, it turns out that they had really no modern tools at all. In fact, they had virtually no tools whatsoever. However, they did have mathematics, which was essentially their only tool. And armed with mathematics, they managed with amazing accuracy to determine the size of the moon, of the Earth, of the sun, and the distances between the Earth and the sun and the Earth and the moon. They did that with mathematics. One of the main things they did in mathematics is something that's probably a blast from the past for you people to remember high school, but you probably do remember the phrase similar triangles. That's about as tough as this is going to get, so don't worry. Similar triangles are really quite simple. 2 triangles are similar if they have the same shape, but not necessarily the same size. So you can have one which is a shrunken or blown up version of the other one, but they have the same shape. Here's an example of 2 similar triangles, a small one and a big one. You can see that if I were to magnify the one on the left, it would look like the one on the right. And what I meant by proportionality is simply this. AB is 1/2 of DE, then AC will be 1/2 of DF, and so on. So the corresponding parts will have the same proportions. That's really all there is to it. Those are similar triangles. You will see in the right hand, a tool this simple can be very, very powerful indeed. So, as I just pointed out, you blow one up or shrink one down, and the triangles are similar. Okay, thank you, Connor. It was a tease. It was a tease. Okay. Just a moment ago, I claimed that the Greeks had essentially no tools other than mathematics to aid them in their study of astronomy. Well, I fibbed a little. It's not entirely true. They did have a device which was a crude clock, calendar, compass, sextant, and car alarm, apparently. There you go. This device was called a gnomon. It adds comic value, people. That's what it does. So this was the device, a really amazing thing, was called a gnomon, and the gnomon was a stick. Honest, it was. And here's a picture of a gnomon. You take a stick and you stick it in the ground vertically, and you look at its shadows. When the gnomon grew up to be a bigger stick, it grew up to be a sundial. And in fact, the thing that protrudes in the center of a sundial still bears the name gnomon. And it comes from the Greek for that which has knowledge. Okay, the gnomon. You take your stick, you put it vertically in the ground, and you observe and measure the shadows that it casts during the day. You're all familiar with shadows during the day. These are normal things. So at sunrise, well, sunrise is in the east. You get a long shadow in the westerly direction. As the day progresses, the sun rises in the sky. The shadow gets shorter and curves around towards the north. By the way, throughout, I'm assuming that we are north of the Tropic of Cancer, but I could change this for your current location if you wish. But we're sticking to the north of the Tropic of Cancer. So that's what happens, and then, of course, wrong direction, look at that. And later in the day, the shadow would begin to lengthen again after a certain point, and near sunset, when the sun sets in the west, we have a long shadow pointing in the easterly direction, and there it is. Well, all of you would say, well, this is hardly news, this is hardly shocking, why are you making a point of this? Well, I'm making a point of it because you can learn a whole lot from this stick if you're sufficiently clever. And I'm about to show you some cleverness. Well, you are sitting there staring at your stick, and you're measuring the shadow, and on any given day, the time when that shadow is the shortest, that's noon, that's local noon, that is high noon. High noon because the sun is the highest in the sky. You have time on your hands, so you repeat this daily. You do it every, thank you, you did it? Okay, but we'll give you credit. If you do this repeatedly, day after day after day, it turns out that the longest noontime shadow happens on the winter solstice, and the shortest noontime shadow happens on the summer solstice, and the days directly between the solstices, those are the equinoxes, so this stick is not just a crude clock, it's in fact also a calendar. Well now, on the solstices, either one of them, if you look at the direction of the shadow at high noon, you will see due north. That is geographic north, not magnetic north. And on top of all of that, so this is actually a compass as well, but that's not good enough for you. On the solstices, if you measure the angle of the elevation of the sun from the stick, you can deduce your latitude. So it is in fact a sextant. In other words, you can learn a great deal from this stick if you're clever, and I think by now you've observed that the Greeks were indeed clever. Okay, I was making a whole big fuss about solstices, and you're saying, what's with the solstices? What's all that about? Well, I want you to see the following picture. I hope this helps you. You are looking here at, clearly not to scale. Here's the Earth at the summer solstice in the northern hemisphere, and the winter solstice in the northern hemisphere. They're going around this direction, viewed from due north. There's a little arrow there. And you're looking at two planes. The horizontal plane is called the ecliptic. That's the plane of the orbit of the Earth. The center of the Earth goes around the sun. That plane is swept out. It's called the ecliptic plane. There is another plane, which I've drawn vertically, perpendicular to that. That is the plane that contains the axes of the Earth. You can see the axes drawn there. And is also perpendicular to the ecliptic. Now, on the solstices, exactly on the solstices, that plane, that vertical plane, passes through the center of the sun. And that happens then and only then. I'm willing to bet that all of you have heard on the news, on the summer solstice or the winter solstice, they say, oh, and summer will arrive at 7:32 p.m. And you say to yourself, excuse me, 7:32 p.m.? I thought this was the first day of summer all day long. What happens at 7:32 p.m.? What happens at 7:32 p.m. is that the center of the sun contains that plane. It passes through the center of the sun at that moment. That's what happens. And there's a similar thing I could say about the equinoxes, but I've tried your patience long enough. So the other thing about the solstices is on the solstices, the shadow of the gnomon line up with the meridians. And that's why you get true north on the solstices. Okay, so you can read what I've just said to you, but there it is. Not everything was deduced. There were observations and assumptions. It's obvious. The first things that they assumed is that the Earth was in fact a sphere. The evidence for this is pretty clear. The first observation that makes that evident is when you see a ship go out to sea, it disappears whole first and mast last, right? So the hull disappears over the horizon, but the mast is the last to go. And sailors on ships saw, conversely, if they were approaching an island with maybe a mountain on it, they would see the top of the mountain before they saw the bottom of the mountain. So it was evident that we're looking at some sort of spherical object here called the Earth. On top of that, we know when we have the the lunar eclipses, we are looking at the shadow of the Earth on the moon. Well, guess what? It's round. So it's curved and it's round, and that kind of smells like a sphere to me. So they knew that it was a sphere. They also knew that the moon was a sphere. It's pretty clearly a sphere, but the shading during the phases makes that obvious. If you look at the shading, and particularly the crescent shading, it makes it evident to you that part of the protrusion of the globe of the moon is obscuring the sun's light from making the entire disk shine at once. If it weren't, if it were flat, you'd have a new moon, you'd have no light at all because the moon was opaque. And when the sun came around to the other side, you see suddenly a full moon. You wouldn't see phases in between. So it's observably a sphere. They also assumed that the sun was very large and very far away. That doesn't take all that much to guess. But a solar eclipse makes that clear as well, because clearly during the solar eclipse, the moon is in front of the sun, and so that means that the sun better be farther away and better be bigger. Okay, that's the basis, and now we're going to enter our first hero here, Aristarchus. He's the one in the middle. I want you to imagine, and I specifically want Joe to imagine, a police lineup in ancient Greece. The guy in the middle did it, right? Okay, so that is in fact Aristarchus, and those are his dates. He was extraordinarily smart guy. And he took the very, very happy coincidence that the moon and the sun have the apparent same size, and he ran with that idea. Now, I mean apparent same size, they're clearly different. But you know during a solar eclipse that the face of the moon almost perfectly obscures the face of the sun. So the size, the apparent size of the two is virtually identical. And they both subtend roughly 1/2 degree of arc. What do I mean by that? If you look at the moon and you extend full moon, make it a full moon, extend your hand to the very base of the full moon, and then rise it up slowly to the top, your hand will have gone through 1/2 degree of motion. And you could do the same with the sun, except you'll draw lines that don't do that. But with the moon, you can see that you get 1/2 degree of arc, and the same thing occurs with the sun. Okay, so a tiny bit of geometry actually tells you that if you know that, if you have an isosceles triangle with a 1/2 1/2 degree at the apex angle, you can deduce what the altitude is, and that tells us that the shadow that is cast by the sun of any object is in fact 108 times longer than that object itself. And that is true of the Earth itself. So here, over here, way out there, you've got the sun. Here is the Earth. Here's the diameter of the Earth, AC. This cone is the shadow cone of the Earth cast by the Earth itself. And the length, that altitude is 108 times the diameter of the Earth. So 108 times AC is that distance of that shadow. So it's a whopping big shadow that we cast in the solar system. But the 108 is an important number. So Aristarchus, you remember him in the middle, he deduced the size of the moon as well as the distance from the Earth in terms of the Earth's diameter. How did he do this? Well, he waited around for a lunar eclipse. And then, when the lunar eclipse began, he measured how long it took the moon to just enter the shadow of the Earth to be entirely obscured by it. So how it starts when it just touches the shadow, and click his Rolex watch when the moon was completely obscured. Then he measured how much time it took for the moon to begin to emerge. And he discovered that, that's the picture here, so the moon starts here, it enters the shadow, it goes through the shadow, and it emerges from it. And he measured it, and he discovered that the moon spent 2.5 times longer crossing the shadow than it did entering the shadow. A moment's thought brings him to the following idea. This tells us that the diameter of the moon is in fact, the width of the shadow is in fact 2.5 times the diameter of the moon. Right? If you take that amount of time, it's moving at a uniform speed, and so the path of transit is 2.5 times longer than the diameter of the moon. Then, my handlers have me on 5-second delay, lest I say something too mathematical. So, you are looking at this picture, and I'm going to say the following about this picture. Embedded in this picture are 3 similar triangles. You remember that from about 5 slides back. One triangle is 2.5 times the size of another triangle for the reasons that I've just explained to you. And a little bit of cleverness, actually a lot of cleverness and a little bit of arithmetic, brings you to the conclusion that you can get the size of the diameter of the moon as well as the distance from the moon to the center of the Earth in terms of the Earth's diameter. Here is the diameter of the moon, here's the distance to the Earth, and anyone who wants further explanation about that, you can ask me afterwards. So that's about as painful as it's going to get. But I assure you that that's what he did. Okay, so he has now determined the diameter of the moon as well as the distance to the moon in terms of the Earth's diameter. Well, he didn't rest there. He thought, what about the sun? I've done enough with the moon, let's try the sun. He obviously understood that the moon was not producing light of its own. It was reflected light from the sun. That's clear from the phases of the moon. That's obvious, right? So he said to himself, okay, we have this moon and we have it doing these phases. When the sun is over there and the moon is also over there in the same direction from the Earth, we have a new moon. So we don't really see the moon illuminated at all. The moon goes around a little bit and we get a crescent moon. It goes around halfway, we get a half moon. A bit more, we get the gibbous moon. And when it does 180 degrees to the other side, we end up with a full moon. Well, he realized that halfway along, when the moon is in half phase, we have half a disk, that we're going to have a right angle, a right triangle. And a right triangle is going to look like that. So when the moon is in half phase, if I take the center of the sun, the center of the moon, and the center of the Earth, you've got yourself a right triangle. And that is the right angle right there. Moreover, you'll remember that distance is something he's just finished measuring, so he knows that. Okay, so he said, okay, what if I could get this angle right here? Now that's a little tricky thing to measure, but he did. And he got 87 degrees. He was off by a little bit. The true number is in fact actually 89.85, but give him a break. That's a hard thing to measure, and that's not exactly that terribly wrong. But if you go back to this picture, you can see that knowing that angle gives you a right triangle whose angles you all know and one side you know. So by similar triangles, you can deduce the distance from the Earth to the Sun, which is what he did. And when he was all done with that, he said, what about the size of the Sun? And he said, you know what, I'm really good with these similar triangles. Let me do it again. So we have a small triangle and a big triangle, and those guys are similar because I've made a point of saying that they all have apex angle 1/2 degree. So if I know the size of the moon and that distance, and now I've just learned the size of the Sun, well, one thing left is the diameter of the Sun. I can easily compute that. So he got, incredibly, the size of the Sun, the size of the moon, and the distances between the two of them to Earth, all of that as a function of the diameter of Earth. There's a problem. We're missing one important piece. I would love to know the diameter of the Earth, because everything would then fall into place completely. Because everything I've just said depends on my knowing the diameter of the Earth. If only we had that missing piece of information. Help is on the way. Enter Aristophanes. He's on the left. Yeah. And there he is. Okay, that's Aristophanes. Well, he was a brilliant mathematician, unlike all the others, right? Some of you may know that name, Aristophanes, particularly the mathematicians here. You may remember the sieve of Aristophanes. That's the guy, the sieve of Aristophanes. He was, came up with a method to determine the diameter of the Earth. He learned that, oh, back up just a second. He was also the chief librarian at the Alexandria Library. Now, Greater Greece encompassed also Alexandria. Alexandria is on the Nile Delta as it flows north and empties into the Mediterranean. And at Alexandria, there was the Great Library of Alexandria, which was at that time really the repository, the greatest repository of Western knowledge at that time. It was destroyed later, but that's a story for another day. But in any event, that was the Great Alexandria, the Great Library at Alexandria, and he was the chief librarian there. And he learned that pretty much due south of Alexandria on the Nile, there was a town called Syene. Syene. Syene, by the way, is where it's currently called Aswan, where the big dam is, but then it was called Syene. And the people there noticed that there was a water well that on the summer solstice, the water at the bottom of the well was illuminated by the sun. Now, most people don't see that all that often. So let me just show you what you see. This is what a standard water well looks like. I don't imagine people running to water wells all these days in New York, but there's one. If you look down your standard water well, you will see pitch black at the bottom. That would be what you'd see. However, if you happen to be in Syene on the summer solstice at high noon, when you look down, you can in fact see the water at the bottom of that. So, put all that together, and Eratosthenes said, you know what? Syene has got to be lying directly on the Tropic of Cancer. Otherwise, that wouldn't be happening. Smart guy. So he said, you know what I'm going to do? I'm going to wait for the summer solstice. And I'm going to stick around here in Alexandria, and I'm going to take my gnomon, my stick, and I'm going to put it in the ground vertically. And at high noon in Alexandria, I'm going to measure the angle of the sun on the summer solstice. Because I know what's happening down there in Syene. The sun is directly overhead. So I want to see how it's different up here in Syene. He measured 7.2 degrees. He then took as an assumption, which is a reasonable assumption, that the sun was huge compared to the distance from Syene to Alexandria. And so even though the sun was round, he said, okay, the rays of the sun are essentially parallel lines. They're not really parallel lines, but they're good enough for me. So he took the rays of the sun to be essentially parallel, and he came up with, I'll skip that slide, I'll say that in words later on, but it's there for completeness' sake. I'll just say a few words about it. He recognized that the angle that he was measuring, is 7.2 degrees, is in fact also equal to the central angle of the Earth. I have a nice picture that will make that clear to you. And he deduced that the ratio of that angle to the entire angle, 360 degrees, was as the distance from Syene to Alexandria was to the circumference of the Earth. So let me give you my first pretty picture. Here's my first pretty picture. Here's the Earth. Here's my stick at Alexandria, not to scale. Here is my well at Syene, and the sun is coming directly overhead, illuminating the base. Here we have the parallel rays of the sun, because the sun is gigantic. And the second thing which you're going to remember from high school after you remembered similar triangles is the following quote. It's the last time I'm going to do this to you. Parallel lines cut by a transversal form alternate interior angles that are congruent. Now, that may ring a bell to some of you, that may cause pain to some of you, but in any event, it's true. So, deal with it. In particular, that's the angle he measured, 7.2 degrees. That was the angle of his elevation of the sun where he was. But he said, wait a minute, I know about alternate interior angles. So that means that that guy is 7.2 degrees as well. That's the central angle in the center of the Earth. Okay, so here's what I've done. I have taken the words, I have taken the numbers, I've taken everything away from what I've just said, and I've left the logic. So if you like, this is essentially a grin without a Cheshire cat. That blue, that's the angle I know, that's 7.2 degrees, that's the angle at the center of the Earth. And that blue angle is to that blue distance, the distance from Syene to Alexandria, as that green angle, that's the 360 degrees, is to that green distance, which is the circumference of the Earth. So I've made two fractions that are in fact equal. Solid blue is to dotted blue, as solid green is to dotted green. And the fact of the matter is I know three of those four things. And the thing I really, really want is that dotted green. Well, if I know three of the four things, I can figure out the fourth one. So he got the circumference of the Earth. And 2 slides back, I told you that he got this number, which was correct to within 2.3 percentage points, which is pretty darn good, I must say. And then he needed, of course, to get the diameter of the Earth, but that's a piece of cake. You know the circumference. You know the circumference is pi times the diameter. You just divide the circumference by pi, and you get yourself the diameter. By the way, Archimedes has just finished computing pi to some unbelievable number of digits, doing some shockingly clever things. Archimedes was actually smarter than both of these guys, but that's another story. In any event, we now have D. That was the missing piece. That's what Aristarchus needed, and everything now fell into place. So putting this all together, we can plug in this value, the diameter of the Earth, into the earlier results of Aristarchus. And now we know the actual distances between the Earth and the Moon, the Earth and the Sun, and the sizes of the Moon and the Sun. There are weak links here. And the weakest links in all of this stuff, even though the ideas were absolutely stunningly brilliant and the logic was completely pristine, well, measurements. If any of you have ever been in lab, any kind of lab, you know measurements is the downfall, right? It's where it all falls apart. I told you that Aristarchus was measuring the time that it took the Moon to do this and that, and I made a little joke about his Rolex watch. This is his Rolex watch. The Greeks had a water clock. This is what he did his measurements with. I don't imagine it's accurate as a Rolex. Maybe a Times Square Rolex for $5, but that was another issue. Worse. I hesitate to tell this story, but I'm going to do it anyway. It's almost certainly false, but it's so good it deserves to be true. And so I'm going to put it out there, and I want you to enjoy the fact that it deserves to be true, even if it's bogus. I told you that Eratosthenes measured the distance from Syene to Alexandria. You needed to know that. You would have thought that all the other things he did were hard, and this was easy. That was the hardest thing he did. So what did he do? The Nile is a trade route, and those days trade was done by camel caravan. So he went to some camel drivers who plied the trade route from Syene to Alexandria, and he said, how many days does it take you to do this? How many hours a day do you walk? And by the way, how fast does a camel walk? And so he measured the speed of a walking camel. He put all that together, got the distance from Syene to Alexandria. As I say, that camel looks sufficiently supercilious to not believe this either. But there it is. So you like that story, you don't like that story. I put it out there for your amusement. But all of those things were, of course, the weakest link. But the ideas were absolutely, positively brilliant, and the logic was pristine. So these were really brilliant results nonetheless. And we can see that armed with an analytical mindset, the Greeks used these tools of deductive reasoning to conclude with incredible accuracy, the sizes of the moon, the earth, and the sun, and the relative distances. Well, there's only one thing I have to say here, is we can only respond with awe. And at that, I thank you so much for listening. And now I'm happy to entertain any questions that you might have involving similar triangles or alternate interior angles or camels or anything else. Does anyone have one, Joe?
Actually, I have a question about Alexandria, which was, why did that
Well, it was on a trade route. It was a very important trade route. It was also near. Well, it was Greater Greece at that point. It was Greater Greece. Greece expanded their area.
That was formerly Egyptian.
It sure was. And we know that Archimedes was in fact born in Sicily, so he was an Italian actually. But that was part of Greater Greece as well. And this was on a trade route. And what people did then, apparently travelers passing through that trade route area, it was also a port because it's on the Mediterranean. So it's at the mouth of the Nile, and it's on a port. So you've got both of those things, the ships coming up and down the Nile, you've got caravans, you've got ships from the Mediterranean. A lot of travelers pass through, people traveling on camels. And what they would do apparently is they would confiscate scrolls that people had with them, copy them down with their scribes, and then give it back to these people so that they would amass all the knowledge that they could get their hands on. And so this became a huge repository for Western knowledge at the time until it was burnt to the ground. It was unfortunate, more than unfortunate, shocking. But in any event, that's what it was. And it was a brilliant center. And a lot of the great names that you know from Greek history, they studied at Alexandria too. Other questions? Yeah. Conchetta. Probably not. First of all, it was in Greek, but beyond that, I imagine that they were able to describe what they were getting at in a rather lengthy way. I'm sure they didn't have the shorthand that we have. They also did not have trigonometry as we know it. So all that stuff that you were thinking about, oh, take the sine of that angle, oh, no. They had pre-trigonometry where they were dealing with chords of circles. So the trigonometry that we know today came quite a bit later, but they did have similar triangles. So based on a similar triangle, if you take a triangle and you know its angles, and you know one leg of it, you can make a model of that guy. You can take that and you can make a small one by measuring it, and then you can measure that stuff on paper. So you could say everything you need to know about that triangle just by knowing similar triangles. So that's what they did. Other questions? Yeah.
Was there a motivating factor for this kind of intellectual pursuit? Was there a practical application?
The Greeks were rather different from most of the cultures at the time. The Greeks were not alone. There were many other cultures that did fantastic mathematics. The Babylonians certainly did. The Indians certainly did. The Egyptians certainly did. Most of those, however, were motivated by practical things. And when the decline of the Greek Empire was pretty much handed off to the Romans, that shift became clear. The Romans were extremely practical. We want our aqueducts to carry water, and we want our temples to stand up, and all that stuff has to happen. So it wasn't just architecture and functionality. The Greeks had a quasi-religious relationship with mathematics. mathematics. They really, really did. And they, for example, they came up with the idea of perfect numbers because the idea of a perfect number struck them as perfect, right? So it had, as I say, the motivation was quasi-religious. That this is just pure and right and beautiful. And as far as I know, it's one of the few cultures that had that view of mathematics. That drove it. That really drove it. Naturally, they did practical things as well, but that's really what drove these things. Like, I'll tell you a small short story about that. The Pythagoreans believed that the Pythagoreans were a brotherhood of mathematicians, not just Pythagoras. He was sort of the head honcho, but there were others there. And they believed that all real numbers were rational numbers. All numbers were rational. They didn't believe in irrational numbers. One of their members proved that the square root of 2, that's the diagonal of a 1 by 1 square, was an irrational number. It was absolutely stunning, brilliant proof. To reward him, they took him out to sea and they threw him overboard. And they did that because he violated their view of what should have been. We want all numbers to be rational, and you showed us that we're wrong, and we're not going to go for that. So you're going to sleep with the fishies. So that gives you an idea. Other questions, anyone? Yeah, Frank.
I'm just curious, so when they came to these discoveries,
Yeah.
Did that generate any kind of tension at the time, or is it something somebody dug up and put hundreds of years afterwards?
Well, it did generate attention, but it also, a lot of it disappeared. A lot of it was recorded. But Aristarchus, who was my first hero, the one in the middle, he in fact proposed a heliocentric universe. And that vanished. It got overridden by Aristotle and others, and so it went back to the Earth being the center of the universe. And it wasn't until we got Copernicus that said, well, maybe Aristarchus was right here. There is an issue of that. It's an amazing thing with the growth of knowledge in humanity. Certainly isn't linear, and it's worse than not linear. It doesn't even proceed in the same direction. It goes backwards sometimes. Knowledge gets lost. When Columbus set sail, his understanding of the circumference of the Earth was flawed, radically wrong. If he had listened to Eratosthenes, he wouldn't think he's in the West Indies. He'd say, wait a minute, I'm nowhere near there. That can't possibly be right. But he got it wrong. He misunderstood, or he lost what Eratosthenes had to say. How that happened, I have no clue. Why that's wrong. Worse, the sailors on his ship thought the Earth was flat. My goodness, so we have dragons and sea monsters and flat Earths, and we don't know the diameter anymore. And these people knew all of that. So how things disappeared, I can't begin to tell you, but they did. They did. It's a shocking thing. Joe.
I actually have a technical.
Oh, okay.
It's not that loud.
Okay, well, they can laugh, okay.
It looked like one of those early slides. It looked like it was almost triangles and things like
They did. They did.
I'm just getting from the picture.
Apollonius wrote a treatise on what's called the conic sections. And a conic section is, well, actually, this is not a cone. Well, actually, in real life it is, because it's three-dimensional. So the cross-section of a cone is a triangle. But in real life, you're right, it's a cone.
And they were the first to...
Yes. Apollonius did that. So if you take a cone and you slice that thing with a plane, depending on the angle of slice, you get a circle, an ellipse, a parabola, or a hyperbola, depending on the angle of the slice compared with the slide angle of the cone. They knew that too. Yeah, they knew a whole lot of stuff. Oh, yeah, amazingly so. Other questions? Anyone? Ah, yes. Gene.
So, once Aristarchus shows the distance, you see how fast something has to go to get around. Is that one of the things that led him to
No. First, what makes the sun go around every day is not the distance of the sun, it's the Earth's rotation.
if the sun would go,
Oh, I see.
maybe it's
Right. I think what motivated him was this. He felt that the sun was so gigantic that it's probably playing a bigger role in the solar system than we are. It's so much bigger than we are. It surely has got to be dominating what's going on out there. That was his point of view. So it wasn't more than the speed of that, but it was really the dominance by size. Other questions? Okay, in that case, I thank you all for coming. Okay. Stick around.